Hello everyone, this is chapter 15. In this lecture, we are going to talk about acceptance sampling methods for attributes kind of data. There are also other kinds of sampling techniques rather than acceptance sampling, and also there are some acceptance sampling methods just for variable kind of data. But in this lecture, we are not going to deal with them, we are not going to cover them. You can refer to chapter 16 for this purpose. In this lecture, we have acceptance sampling techniques and we are dealing with the attributes. Alright, up to here in this course, we have reviewed control charts, process capability, designed experiments, and process optimization. With these tools, we are just dealing with the processes, input variables of the processes, output variable of the processes, etc. But acceptance sampling is different than these methods. Why? Because in acceptance sampling, we are dealing with the lots. By lots, I mean a lot means a group of a set of products. Okay, so we are dealing with a group of products in acceptance sampling. And by sampling, I mean we are going to take some sample from the lots, then we are going to accept the lot or we are going to reject them according to the number of defectives in the samples. Okay, that's why it is called acceptance sampling. Let's proceed, but before proceeding, let me also say this. Maybe you can remember from the lecture 1 or lecture 2, I think. We have said that we can rank the methods we're going to use in this class according to their impact level on the quality improvement. And in this ranking, designed experiments takes the first place, then control charts follow, then we can put the acceptance sampling. Why? Because in acceptance sampling, we are not dealing with the processes, we cannot control them, right? We cannot improve the quality of the processes. That's why the impact of the acceptance sampling on the quality of the processes is limited, but it doesn't mean that it is not significant. It is important, it is very important, but the impact of the acceptance sampling methods is not as much as the designed experiments and control charts. Remember it, alright? So what are we doing in acceptance sampling? In the application of acceptance sampling, we are taking lots, then we are making a decision. This decision called lot disposition or lot sentencing. In lot disposition, we are accepting or rejecting a lot, right? So to reject or accept the lot, we are making some inspections on the lot, then we are making that decision, accept or reject. Accepted lots are put into production, and rejected lots may be returned to the supplier or returned to the previous processes if you are talking about in-house application of the acceptance sampling, in plant, in factory application of the acceptance sampling. And also we can also take some lot disposition action like rectifying action, and we can make some corrective action, then we can correct the lot, and we can accept that previously rejected lot. Maybe we are going to see these actions in next slides. There are three aspects of the sampling that are important. The first one, the purpose of the acceptance sampling is not estimating the quality of the processes. Okay? In acceptance sampling, we are just making a decision about the lots, accept or reject. That's it. And from the acceptance sampling plans, we cannot make any inference about the quality control of the processes. We cannot make this. okay? And even if all lots are of same quality, sampling will accept some lots and reject others. For example, you have taken 2 lots, and from the lot 1, you have taken a sample, okay, from the lot 1, and you have put it and inspected that sample, and you have found, let's say, 3 defective units. And you have taken another sample from the lot 2, and you have inspected that sample, and you have found 0 defective units. There are just 0 defects. It doesn't mean that lot 2 is better than lot 1. You cannot say this because you are making sampling. You cannot talk about the population, which is here the lots, okay? Maybe both of these lots have same number of defective units, but because you have taken some sample and you have just inspected a fraction of the lots, you cannot make any judgment about the rest of the parts in the lots. Okay, that's it. The third aspect is we can talk about the most effective use of acceptance sampling is not to inspect quality into product, but rather as an audit tool to ensure that the output of a process conforms to requirements. So it's just an audit tool. There are 3 alternatives for lot disposition. We can make no inspection, then accept all lots or reject all lots. The second alternative, we can make 100 inspection here. It means that we are just gonna take all of the items in the lots, then we are gonna inspect them. But third alternative, which is we are talking about right now in this lecture, it is acceptance sampling. In acceptance sampling, we are gonna just take some samples from the lot, then we are gonna inspect them. We are not gonna inspect all of the items in the lots, okay? And when this is useful in practice, the situations as follows. When testing is destructive, for example, if the inspection is destructive on the product you are handling, you can go with the acceptance sampling rather than 100% inspection. Why? Because it will ruin your products, okay? The second one, when the cost of 100% inspection is extremely high. Why? Because you are taking all of the items and then inspecting them. So it will be more costly. The third, the 100% inspection may be timely, inefficient, okay? The fourth one, also in 100% inspection, you have some inspection error you can make. So if this error rate is high, you can also go with the acceptance sampling. And the fifth situation, maybe your supplier has an excellent quality history. Let's say your company, your supplier is a Six Sigma company, for example, and you know that by their excellent quality history, you don't need to inspect all of the items in their lot. So maybe you can also go with the acceptance sampling. And maybe in some cases, maybe you can also go with the no inspection if you just rely on them, if you count on them. And the sixth situation, even if your supplier has an excellent quality history, maybe you cannot go with no inspection. You need to make acceptance sampling because there will be some product liability risks. And if there are some product liability risks, it means that every partner in a supply chain will be responsible from the defective units. That's why you need to make acceptance sampling rather than just no inspection, even if the supplier is very good. Okay. Let's continue. When we compare the acceptance sampling with 100% inspection, acceptance sampling has some advantages. Because it has less inspection, it would be less expensive, and there will be less handling of the product, so we will reduce the damage. And acceptance sampling can be applicable to destructive testing. It will require fewer personnel, and it will also reduce the inspection error because we are not making inspection all of the items in the lot. And lastly, the last advantage, when we reject the lot, we will not just return the defective unit, we will return the whole lot to the supplier. And when the supplier knows that, they will try to minimize the rejection probability of their lot, so they will try to increase their quality level. Right? And besides disadvantages, acceptance sampling has also disadvantages. What are they? The first one, we have some risks for making acceptance sampling. Why? Because when we make the judgments on sampling, the samples, maybe we can accept the bad lots or reject the good lots. How? For example, you are taking a sample from the lot and you are inspecting the items in this sample and you are rejecting the lot, for example. Okay, so you have counted the number of defectives in the lot and it is too much, then you reject it. But maybe the rest of the lot does not have any product in it. When you do that, actually you are rejecting a good lot, maybe. And there is some probability you can make this mistake. Okay, and this is called alpha error in this case when you reject the good lots. And if you accepting the bad lots, this risk is called beta error. Okay, and these errors are coming from the sampling we are making in the acceptance sampling method. The second disadvantage is we are getting less information on the lot because of the sampling. And the third one is acceptance sampling requires planning and documentation. Earlier we said that acceptance sampling is not about processes and they cannot directly affect the process output. But when we think about the loads, general loads and a stream of loads, okay, and when we think about this population and the information we are getting from the acceptance sampling can be used in processes too. So, for example, if you are getting so much, rejected lots, so maybe it may mean that the process output is not good. So process output quality is not that good. So supplier can improve itself and improve the process quality level. Then they can also produce the more accepted lots. Okay, so indirectly, acceptance sampling will affect the process output. In acceptance sampling, we will have some plans and we will do our analysis on these sampling plans. What are these plans? These plans are single sampling, double sampling, multiple sampling, and sequential sampling. In single sampling, we are just taking one sample. In double sampling, we are taking two samples. In multiple sampling, we will take several samples. And in sequential sampling, we will see in next slides the sequential sampling. It is also like multiple sampling. And about the sampling plans, an important indicator is the average amount of inspection, because we will try to reduce the number of inspection in the acceptance sampling, right? That's why we are not making 100% inspection. And average amount of inspection is a good indicator to efficiency of the sampling plans. And if we, get the same results with different plans, with different amount of inspections, average amount of inspections, we are just gonna select the minimum amount of inspection with the sampling plan, because it will also create the equivalent results with the other plans, but we will reduce the amount of inspection. Okay, so we will increase our efficiency in acceptance sampling. So this is the important criteria we are using in the sampling plans. So we will choose one of the sampling plans, or maybe we can change these plans according to the lots, according to the situation, okay, according to the case. But we will try to minimize the amount of inspection. Let's continue. Load formation and random sampling is also important in acceptance sampling. Random sampling is very, very important, because otherwise you cannot make acceptance sampling methodology, because it will not make any sense if you are not using the random sampling. If you are using your judgment to select the items from the lot to create the samples, you don't need to use acceptance sampling method. It will not make sense. Okay, so you need to use random sampling. To use random sampling, you need to form the lots according to that, and lots must be homogeneous. It means that the products in a lot must come from the same machines, same operators, or if it's possible, they must be produced within the same time period. And larger lots are more preferred to the small ones, and lots also should be conformable to the material handling systems, so we will not make any harm to the products in it. So for random sampling, we need to number the products in it, then we need to choose these numbers randomly from the lot. There are different ways to do that. For example, one of them is the stratification. Stratification is making cuts, making layers on the lot. So this is the stratification. So we are making a layer here, and these are also different layers. All right. So when we create this kind of cubes in the lots, so we can also randomly select these cubes, okay, and we can inspect that items in this randomly selected cubes in the lot. All right. Here the main idea is this: random sampling is very, very important. All right. Do not use judgments on selecting the items from the lot. Okay. Use random sampling. It's so important. How can we use acceptance sampling methods? We have a table here, but maybe you are not familiar with these terms, with these methods right now. When you finish the lecture, just return back to that table and observe it again, okay? But let me say this. We are selecting the attributes procedure or variables procedure when we are making acceptance sampling. We are not dealing with the variables procedure right now. You can check the chapter 16 for this purpose. We are dealing with the attributes kind of data right now in this lecture. So according to our objective, with the acceptance sampling, we will, choose our procedure to make the acceptance sampling method. For example, if the objective is to reduce the number of inspections after good quality history, we can use skip lot sampling or double sampling, for example, because we are wanting to reduce the number of inspection. It will be more efficient. Why we want to reduce the number of inspections? Because we know that the supplier has a good quality history, so we can reduce the number of inspection because we can rely on them. All right, and other objectives are here also. Before proceeding, let me remind you again, when I'm saying supplier, this supplier can be an external company, a supplier company, or it can be an internal process if we are talking about in-house application of the acceptance sampling, okay? And consumer will be can be your company, for example, and also can be a process in your company. If you are taking the lots from the previous processes in your company, the following processes will be consumer of these lots, all right? And when you consider an external company as a supplier, your company will be the consumer because you will take these lots and you are going to make the acceptance sampling. Firstly, let's talk about the single sampling plans. Among the plans we have, double sampling, multiple sampling, etc. Let's talk about the single sampling. In single sampling, we are going to take just one sample from the lot. Suppose that we have a lot here and it has 10,000 products in it, and the lot can be represented by the capital N, all right? And we are taking a sample randomly choosing the items in the sample. And in this sample, let's say we have 89 products, okay? And the sample can be represented by the lower N, all right? And after taking this sample, we are going to inspect all of the items in the sample. When we count the number of defectives in the sample, it will be represented by D, all right? And if the number of defectives in the sample is lower than a reference value, we will accept the lot. But if it is greater than that reference value, we will reject the lot. For example, let's say number of defectives is 2 and C is 3. We will accept the lot. But if you have counted the defectives up to 5, for example, if you have found 5 defectives in the sample, you will reject the lot, okay? And how can we determine the C then? C will be determined by the consumer, okay? And we will see how can we determine the C also. An important measure of the performance of an acceptance sampling is the operating characteristic curve. Let me show you an example here. This is the OC curve for acceptance sampling plan according to that sample size and C level. So this curve is just changing by up to the number of samples and the C level. In horizontal line, we have lot fraction defective, and in vertical line, we have probability of acceptance, PA, okay? And lot fraction defective is represented by the lower P here, all right? So OC curves is showing the discriminatory power of the acceptance sampling plan. Why? Because earlier we have said that we are making some mistakes. We have some risks when we make lot disposition in acceptance sampling. Why? We can accept the bad lots or we can reject the good lots, right? So there would be some probability we can accept the lot according to their whole fraction defective in the lot. Maybe we do not want to exact lot fraction defective, but when we take a sample and when we count the number of defectives, and if we do that for multiple lots, for several lots, let's say 1,000 lots, we can come up with a probability of acceptance of these lots. For example, when you take a sample of sample size of 89, and if your reference value is 2 here, okay, and when you use this sampling plan for 100 lots, okay, and if the average lot fraction defective in these lots, these values, you can calculate the probability of acceptance of these lots, all right? So this, I said, this is showing the discriminatory power of the acceptance sampling plan, right? Here we can know that we can calculate the alpha and beta error probability, right? Because, for example, when you have high fraction defective in the lots, the probability of acceptance will be lower. But there are some, cases you will accept the lots, right? Because this is a probability. When you take 100 lots, you will accept some of them, even if they are bad, even if their fraction defective is, high. It means they are bad lots. You will accept them, some of them. You will accept some of them. But also, even if the lot fraction defective is low here, for example, it means that the lots are good, for example, you will reject some of them, right? Because there is a probability here. For example, even if the probability is here so high, you will reject some lots, even if they are good. So this curve will show you the discriminatory power of the sampling plan, okay? Just keep in mind, and you will understand this in next slide. All right? And also we can use the tables for this purpose. This is the curve. We can make it in graph. Also we can use the tabular form. All right? So we have said that this is the probability of acceptance and this is the lot fraction defective P. So how can we calculate this probability of acceptance according to lot fraction defective? We can calculate the probability of acceptance by this way. We can use the binomial distribution. Let me remind you the binomial distribution here. The distribution of number of successes in an N trial with replacement is the binomial distribution. Here, success, it's a general term. In our case, it is the number of defective, okay? We are trying to find the number of defectives distribution in a sample, okay? In a sample N here. When you just consider one isolated lot, if you are calculating the probability of defectives, number of defectives, for just one lot, you cannot use binomial distribution, okay? Because in binomial distribution, we have a condition with replacement. But in inspection, you are not replacing the defective units in the sample and then you are taking another item in it, okay? You are not replacing the products in the sample. That's why when you just consider one lot, you cannot use binomial distribution. You need to use the hypergeometric distribution because it was the without replacement version of the binomial, all right? Just do not forget this. So I said we are going to calculate the number of defectives probability. Then we are going to use this probability to calculate the probability of acceptance in the OC curve, right here. And to accept a lot, we said that earlier in lot disposition, when we count the number of defectives, when it's lower than the C level, reference level, we will accept the lot, right? So here we are gonna find that probability, and that probability is here. The acceptance of probability is probability of the number of defectives will be lower than C, right? And lower than C, when we find this C value, let's say, for example, when we said that the C is 3 and D can be 0, 1, 2, and 3, right? So we need to combine, we need to sum up these probabilities up to the C point here, all right? So this is a cumulative distribution of the binomial, all right? So how can we calculate the individual probability here? We can use the binomial formulation. This is the binomial distribution, PMF, probability mass function, and we can use it. For example, there is an example here. For example, if the lot fraction defective is P, which is P here, is equal to 0.01, it means that 1% of defective, okay? And when the sample size of 89 and when the C is 2, then the probability of acceptance will be the probability of D is lower than 2. Here we have two cases, not two cases, we have three cases. D can be 0, D can be 1, and D can be 2, right? When D is 0, this will be our calculation. When D is 1, this will be our calculation, and when D is 2, this will be our calculation. And when we sum them up, when we calculate the cumulative probability, we can come up with the probability of acceptance, okay, with these parameters. So when the P is 0.01, so this curve will be shows the in vertical line that probability 0.93 approximately. And it means that when the load fraction defective is 1%, okay, load fraction defective is 1%, and if we are taking sample size of 89, if our C level is 2, we will accept the lots with that probability. Okay, with that probability, we will accept the lots. But here, this probability is just for whole lots. Okay, it's a general probability, right? This is expected probability, let's say. So let's continue. So we have said that the curve is changing up to sample size and C level, right? So this curve will be affected by the sample and the C. Why? Because this calculations actually, we are using N and C here, right? We are using N and C here. That's why the curve will change according to the sample size and C level. So how they will change? Let's consider this 3 plus here. In the first plot, we are seeing the ideal OC curve. Ideal OC curve means the discriminating power of the OC curve is, perfect. We can discriminate the good lots and bad lots perfectly. Why? Because up to that point, let's say this, load fraction defective is our target level. Let's say this is our, wanted level in our, lots. And up to that point, we will accept all lots, and after that, fraction defective, we will reject the all lots. Okay, there is no probability here. So it is the ideal OC curve. But because we are making sampling, we have some risks to make. We can have some errors. That's why this ideal curve will not be our case in acceptance sampling method, acceptance sampling plan. These are will be our case. Okay, this ideal OC curve can be obtained by the 100 inspection with error-free inspection error-free. We can get this kind of OC curve, but in acceptance sampling we cannot make it. But we can try to approximate this ideal OC curve. Why? Because we are trying to maximize, we are trying to increase the discriminative power of the acceptance sampling plan. Why are we doing, why are we trying to increase it? Because we are trying to reduce the errors, all right? It will be more accurate. We will not, we will, reduce the probability of rejection of the good lots, and we will also reduce the probability of accepting the bad lots. That's why we are considering OC curves, and we are trying to make analysis on OC curves and try to increase the performance of the sampling plan. For example, in this OC curve, when we increase the sample size, actually we are trying to get converged to the ideal OC curve, right? So it means that when you increase the sample size, you will get more information, so you will not make make errors as much as when the sample size is lower, all right? And also, so when you consider the C level on the OC curve, when you decrease the C level, you will decrease the probability of acceptance. Here you need to find the balance, because when you decrease it so much, you will reject the good lots. You are increasing the probability of rejection of the good lots here. Okay, but when you increase the C level so much, you are increasing the probability of accepting the bad lots. All right, so you need to balance between them. Okay, yeah, so the balance point can be that. Okay, C is 1, for example. All right, so for example, when we take 100 lots and let's say sample size is 89 and C is 2, and assume that the lot fraction defective is 0.02, and it means that 2% of the lots are defective. Okay. When you make this sampling plan, probability of acceptance will be 0.74. So you will accept 74% of the lots and you will reject 26% of the lots. And in this example, we take 100 lots, and according to these parameters, you will reject 26 lots, and it is too much, right? So here, actually, we are making some mistakes. For example, we are also, reject the good lots here. All right. So probability of acceptance affects these risks, and you are trying to reduce these risks, minimize the probability of rejection of the lots when the lots is good, and you are trying to decrease the probability of accepting the lots when the lot is bad. Okay. Let's continue from here. We have already talked about them. Okay. Let's talk about some specifics on the OC curve. In OC curve, here we have thought about a population of lots, right? So that's why we are using binomial distribution when we are calculating the OC curves, such OC curves. Right? So we have thought about the whole population of the lots. Whole population of lots means that we are thinking about indirectly about the processes. Okay, so if we think about whole products coming from the supplier, actually we are talking about the process of the supplier, right? And consumer can consider acceptable point, acceptable quality level on process average of the supplier, and this level will be called acceptable quality level. But here it's important, acceptable quality level is a property of the supplier's manufacturing process, not a property of the sampling plan. All right? But also, when we think about the individual lots, not about the whole lots are coming from the supplier. So individual lot will be finite size, all right? And when we think about an individual lot, and when we want that protection from the individual lots of poor quality, we can establish the lot tolerance percent defective, LTPD. It is called also rejectable quality level or limiting quality level. And LTPD is a level of lot quality specified by the consumer. It is also not a characteristic of the sampling plan. So here, acceptable quality level is the quality level, is the process average of the supplier, right? And LTPD is here the consumer's set value for individual lots. Okay? And sampling plans, we have introduced the single sampling, double sampling, multiple sampling, etc. These sampling plans can be designed to have specified performance at the AQL and the LTPD points. So we will use this AQL and LTPD to construct our sampling plan. In this sampling plan, we will choose the single sampling, double sampling, multiple sampling, etc. according to that point. Also, we will construct the sampling with a set of the sample size. So we will also set our sample size according to that point. And we will also set our C value, the reference value, according to that critical points, specific points. Okay, they are important. So acceptable quality level is the poorest quality level consumer can accept. Okay, and LTPD is the consumer's set value for protection from the individual lots of poor quality. All right. For instance, if consumer may accept, not let's say want, let's say expect. For instance, consumer may expect average acceptable quality level at 1%. Okay, 1% defective. So the consumer will be interested in the lot fraction defective at 0.01 in OC curve. Let's see the OC curve again. If the acceptable quality level is 1% defective, it means that we expect a lot fraction defective at 0.01 here. All right. So we will expect a probability of acceptance on lots here, like in this point. We have already calculated, I think, these values. Where were they? So here, right? Yes. With this specific sample size and with this specific C level, we have calculated it. If we use this sample size and if we use this C value, and if the acceptable quality level is 1%, so it is 0.01, if we use scale 0 to 1, okay? So we will interested in at this probability of the fraction defective in OC curve. So the probability of acceptance of the lots will be approximately 0.93. So it means 93%. So if the consumer expects that acceptable quality level, okay, and for instance, if it takes 100 lots from the supplier, it will expect that 93 of the lots will be accepted and 7 lots will be rejected. Okay, and this will be the acceptable quality level of the consumer. All right. About the lot tolerance percent defect, we cannot use the OC curve because this OC curve it is just about the population of the lots. But also maybe we can use it in some cases. Let's talk about the type A and type B OC curves. Up to here we have talked about type B OC curves. In type B OC curves we were considering the whole lot population. Indirectly we were considering about the process of the supplier. Okay, that's why we have used the binomial distribution to calculate the OC curve values in the type B OC curve. But also, we can also construct another type of OC curve, and it will be about the individual lots. Okay, individual lots. And when we think about the individual lots, we need to use hypergeometric distribution. Okay, because of the condition of without replacement condition. Okay, so we need to use the hypergeometric distribution if we are considering the individual lots. So LTPD can be specified only on the type A OC curves. Okay, but also we know that if the sample size and the lot size fraction, this proportion is lower than 0.10, it means that the lot size is 10 times of the sample size. If this is the case, type A and the type, not the C here, type B OC curves will converge to each other. Let's change it. Let's see, this B. Sorry, excuse me. All right. Okay. So, and also we see here this type A and type B converges to each other. Okay, if the sample size is just 10% of the total lot size. All right. So acceptable quality level can be found in type B OC curves, and LTPT points can be found in the type A OC curves. Okay. And also let's talk about the other aspects of the OC curve behavior. We have seen here two plots, and in these two plots, maybe you notice that we are just considering the sea level is 0. It means that when we encounter just one defective unit in a sample, we will reject the lot. All right, this is the case. So we do not tolerate any defective units. In this case, if we use larger samples, the probability of acceptance will be so much low, right? Even if the acceptable quality level is 0.01, for example, the probability of acceptance is getting lower, right? So we cannot use the usual sampling plans with the case C equals to 0, all right? So for this purpose, maybe we need to search for other alternatives, and one of the alternatives is chain sampling. And you can also find some information, some introductory information about the chain sampling in the chapter 16, okay? And in this second graph, maybe you are gonna notice that the proportion of the lot size and sample size is equal for each curves here. So the lot size is 10 times of the sample size. The lot size 100 and sample size is 10, and here the lot size is 500 and the sample size is 50. So the proportion is 10 and 10 here, and 10 also here. So if we change the sample size according to the lot sizes, and if we keep a constant level for this proportion, actually it will be illogical, right? Because this curve changes rapidly and dramatically when you use this proportion. Even if you get, larger samples, you will fail. How do you fail? Because you will get, low acceptance probability. You will reject lots of even if the fraction defective is not that, low. Okay, even if the lots are good at some level, you will reject lots of them. So we do not want this. So it would be illogical to keep a constant rate for sample size and the lot size. Okay, here in practice, you will try to get lots as much as possible in same amount. Even the lot size differs from each other slightly. You will keep your sample size constant. You are not gonna change your sample size according to proportion of the lot size. All right, it will be illogical, and you are seeing here this illogical behavior here. All right, let's continue. So how can we design a single sampling plan with a specified OC curve? Specified OC curve, I mean when we expect acceptable quality level, and when we set a LTPT point in the OC curve. So how can we design a single sampling plan with this specific point on the OC curve? In order to design a single sampling plan with those specified OC curve and specified points, we need 2 points on the OC curve. We cannot go with just 1 point because we are considering acceptable quality level and LTPD, and also about the risk. For example, we have two kinds of risks: alpha risk and beta risks. Alpha risks was the probability of rejecting a lot when the lot is good, and beta risk was the accepting a lot when the lot is bad. So we have two risks, we have two specific points, so we need to take 2 points consideration on the OC curve to design a single sampling plan. Here, suppose that we wish to construct a sampling plan such that the probability of acceptance is 1 minus alpha for lots with fraction defective P1. Here we say 1 minus alpha because alpha is here the alpha, type 1 error. That's why the probability of acceptance will be the 1 minus alpha, all right? And alpha will be the probability of rejecting, all right? And we are considering here with this acceptance probability here with the fraction defective P1. And the second point, the probability of acceptance is beta risk for lots fraction defective P2. So here we have chosen another fraction defective P2 because this P2 is like the deviated fraction defective. We want the fraction defective at that point, P1, but it will be here. When it will be here, and when they accept the lot, it means that this is the beta risk we are talking about. This is the beta probability. Why? Because we know that at the fraction defective P2 means the lot is bad. We do not want this. But also here we have a probability of acceptance. We can also accept that lots with this fraction defective. So here it is. This is the beta risk. We are accepting the lot even if the lot is bad. So we are accepting the lot when the P2 exists, is present. All right. So we are choosing 2 points in the OC curve to design a single sampling plan. All right. And also we can call this alpha risk as supplier's risk and beta risks called also consumer's risk, because the alpha risk is supplier's risk because we are going to reject the lots even if they are good and supplier need to handle them. Supplier must take the burden of this risk, but beta risk about the consumer because consumer will be the one accepting the lot even if the lot is bad. So this risks on the consumer and alpha risk is on supplier. All right. So because we have selected 2 points OC curve, we need to solve these 2 equations. It is hard to solve it in the OC curves we have observed. So we are going to use another kind of graphs, and this graph is called nomograph. This is binomial nomograph, and we are going to use this nomograph to find the specific points on the OC curve to design a single sampling plan with that alpha risk and with that beta risk. Do I need to mention about something? So generally, fraction defective P1 is the acceptable quality level and P2 is the worse but tolerable quality. That's why we can use LTPT for the fraction defective. Even if the lot can be set, can be called bad in this level, P2 level, we will try to keep this P2 level as much as plausible for the consumer. So we will use LTDP here. And also in here we are going to use the binomial distribution to calculate that alpha and to calculate the beta value. But easily we are going to find those in this nomograph. So to find the specific points, we are going to use this nomograph like this. We are going to take 1 point here, the fraction defective with acceptance probability 1 minus alpha. This is the first point. probability of acceptance 1 minus alpha for lots with fraction defective P1, and the second point will be the probability of acceptance is better for lots with fraction defective P2. Okay, so here we will take that red line, and this red line passes through this ranges here. Here it first passes through the P1 value, okay, and then it will pass through the probability of acceptance here, the 1 minus alpha, okay. And for the second point, we are gonna take that P2 level here, then we are gonna select the beta risk level here, then we are gonna cross lines on these points, then the intersection point of these two lines will give us the designing parameters, okay? So here, for example, it passes through, the intersection passes through, for example, here, when you zoom in, the sample size must be 90 and the sea level must be 3. So we can design our single sampling plans for those two specific points on the OC curve. And when we use the nomograph for this purpose, we get that sample size and this sea level. So we can use this sample size in our accepting sampling method, and we can use this sea level as a reference value to reject the lots or accept the lots. All right. Also, it says the tabular form of this nomograph can be also found in some academic papers. You can check this academic paper in the textbook to find the tabular form of it, right? So let's talk about the rectifying inspection then. In acceptance sampling programs usually require corrective action when lots are rejected. So when a lot is rejected, this lot will be 100% inspected. So we will take all of the items and inspect them, and we will find the rest of the defective units in it. Then we will send them either to rework, or we will replace these defective units with the new indefective, undefective, unconforming products. And this procedure is called as rectifying inspection. Okay. So here, this is the flow of these actions. When you consider, again, lots of lots, okay, the population of lots. So these lots are coming to the inspection activity. Either we accept them or reject them. When we accept the lots, the fraction of the defective will be P0 again in this, like in the beginning. But in rejected lots, because we have replaced the defective units with the unconforming products, the fraction defective will be 0. Then when we combine this rectified lots and accepted lots into just one combining outflow, the outgoing lots will be a fraction defective P1, but it will be less than the P0, P null here, because P0 is the initial fraction defective. Here we have eliminated some defective parts in the rectifying program. That's why the fraction of defective will be less than the initial one. Okay. So how this will affect our specific point, the design points. In this case, if we use rectifying inspections, we are going to use average outgoing quality measure. In average outgoing quality, we will, let's make these calculations here. This is just a plain version of it. So let's calculate the number of defective in the outgoing flow, outgoing lots, all right? But again, I am repeating myself. Do not just here right now, just one lot, okay? Just think about a stream of lots, okay? There are lots of, lots are coming to the inspection. And this is the number of defectives in the accepted lots, right? Why? Because of this. This is the lot size, and this is the sample size we have extracted, okay? In the rest of the lots, we know that there will be a fraction defective at that, right, at that level, P. It is the lot defective fraction. And we will accept this accepted lots with the probability of acceptance, right? This is the probability of acceptance. And the rest of the calculations here, we are taking some information from the rectified lots, right? But we know that when we correct the rejected lots, there would be no defective units in it. So the number of defective units will be 0. And the fraction of the defective units also be 0. Then that part will be 0 then, right? So also we are gonna take this number of defectives on the lots, and we are gonna divide it into the lot size, and by that way we are gonna calculate the average outgoing quality. So we are calculating this average outgoing quality on here, on outgoing lots. All right. For example, if the lot size 10,000 and the sample size 89 and the sea level is 2, then also the incoming lots are of quality with that fraction, 0.0 fraction, so it means 100% defective. All right, and with the probability of acceptance, if this, okay, we know this actually at that lot defection rate, we have that probability of acceptance with this sample size and with this C, right? And then the average outgoing quality we can calculate by the formulation here, and it will be 0.0093. So the outgoing defective fraction will be the 0.93%. Okay, but at the beginning, at the initial, we were having 1% defective. Okay, here in the beginning we do not have the rectifying program, but after we have facilitated the rectifying program, we have reduced the defective fraction in the lots. All right. Let's continue. And also, if the lot size becomes very large relative to the sample size, we can just use this approximation formulation. All right. Here we also see the average outgoing quality limit graph curve. But let us check what is average outgoing quality limit first. Average outgoing quality limit is the worst possible average outgoing quality that can result from a rectifying sampling program. Okay, this is the worst possible limit, and that limit can be also seen here. This is the average outgoing quality limit. Okay, so why this maximum point is the limit for us, upper bound for us? Let's see. If the initial fraction defective is low, let's say from up to here, okay, the average fraction defective of outgoing lots will increase, right? Because we will accept some lots, all right, and we will reject some. But in this rejected lots, we rectified lots, right, and they go back with 0 defects. But with the accepted lots, we have already some defective units. That's why up to some point it will continue to increase, but after some point it will decrease. Why? Because after this point we will have lots of bad lots, okay, and because of this bad lots we will reject them most of the time. Then when we rectify this, correct this lots, and when we replace the good units instead of bad units, we will reduce the number of defectives in the outgoing level, outgoing flow, right? That's why after a maximum point, the average fraction defective of outgoing lots will be reduced. Okay, so that's why the average outgoing quality limit, that point, will be the worst possible average outgoing quality that can result from the rectifying sampling program. Okay, so this tells us that no matter how the incoming defective fraction is bad, okay, average outgoing quality cannot pass that maximum limit, average outgoing quality limit, okay, because of the rectifying, because of the corrective action, okay. Even if the lots are coming with lots of defective, we will reject them most of the time, then we will correct them. That's why in the outgoing flow here, in outgoing flow, in outgoing lots, that we will see reduced number of defective units because we have replaced them. All right. Another important measure for the sampling programs is the average total inspection, because for inspection we are giving our time and also it becomes more costly. That's why also we need to consider the average total inspection. Why? Because let's see here, if the lots have lots of defective units in it, if the fraction defective is high at the beginning, we can reduce them by the rectifying program, right? But this rectifying program means we need to make more inspection. So we cannot rely on the average outgoing quality limit. We need to also calculate the average total inspection. We need to find a balance between the total inspection and the average outgoing quality. So let's calculate the average total inspection then. For calculating the average total inspection, we are going to use this formulation. But first, let us see the reasoning of the formulation. For lot disposition, we need to take a sample, right? And this sample will be size of n. It will consist n items in it, and we are gonna inspect all of these items in the sample. Okay, either we accept them or either we reject them. And if the lot is accepted, this is the number of inspections we are making. But if the lot is rejected, and if we have facilitated a rectifying program on the rejected lots, this will be the average number of inspected units in the rejected lots. Why? Because we have already taken the sample from the lot, and this will be the rest of the lot, and we will inspect all of them if the lot is rejected, okay? And this is the rejection probability. We are talking about the average, then we need to multiply this amount with the probability of rejection of the lots, all right? Let's see it an example here. In this example, the lot size is 10,000. This is sample size. This is the level of C. This is the initial fraction of the defective units in the lots, P. And this is the acceptance probability, okay, of the lots. Then we can calculate the average total inspection. And here for this example, it is 687, okay. And it looks high, right? Because at the beginning, the sample size 89, and we have inspected just 89 units, but with the rectifying program, we need to inspect 687 units on average. Let us see this different average total inspection number with the different lot fraction defective. In this plot, we can see that. And when we increase the sample size, the total, average total inspection increases, right? And when we increase the lot fraction defective, also the total inspection increases, because we will have lots of rejected lots, and we will rectify them. That's why the total inspection, the number of average total inspection also will be high with the high fraction defective. Okay. Average outgoing quality level is an important characteristic, but also when we design a sampling plan, we need to consider also average total inspection, because this is the like a balancing point for our consideration. Okay, we need to also consider about the number of total inspections along with the average outgoing quality level. There are lots of tables, tabular form, scales and specifications for average outgoing quality level and average total inspection, and you can find those tables in Dutch ROMIC plans, and also in the textbook there are some tables, but we are not going to cover them because they are huge tables, but you if you want you can check them. Okay, but just remember that you are going to design your sampling plan if you are making a rectifying procedure with these two metrics, average outgoing quality level and average total inspection. And also, it is possible to design a rectifying inspection program that gives a specified level of protection at the LTPD, that LTPD point, and that minimizes the average total inspection for specified process average P. The Dutch ROMIC sampling inspection tables also provide these LTPD plans. So, in average outgoing quality level, we were considering the incoming stream of lots, okay, the population of lots. Also, we can facilitate this Dutch ROMIC sampling plans, sampling inspection tables, the total, the number of total inspection, etc., with the LTPD. In LTPD, remember, we were considering the isolated lots, the single lots, all right, not about the stream of lots. We were considering individual lots. So also this kind of tables in the textbook also, all right. We were having different sampling plans. The first one was single sampling, the second double, multiple, and sequential, etc. So we have reviewed the single sampling plans up to that point, and we will continue here with double, multiple, and sequential sampling. In double sampling plan, we are going to take two samples, okay? We are going to take one sample, the first sample, and we will make a lot disposition, or we will continue to take another sample. Either we will take first sample, then we will make a lot disposition, and this disposition will be the accept lot. Okay, we can accept the lot, and we don't need to go with the second sample. But if we do not accept the lot, we need to go with the second sample. And also, there is another option, third option. If we reject the lot, also we do not need to go with the second sample. That's why it is called double sampling method. And the first sample, we expect that the size of the first sample will be less than the sample size we use in single sampling plans. Okay, and this is the procedure, the diagram of the procedure. Okay, let's see it here. So we will take a sample. Let's say we have taken a sample size of 50. Okay, and the D1 is the number of defective units in this sample. If this number of defective units is lower than 1, we will accept the lot. Okay, and we don't need to go with the second sample. And if this number of defective units is greater than 3, let's say, this is just an example, okay, this 50 and 3 and 1, these are just examples. Okay, if the defective units is greater than the C2 level is here, 3, we will reject the lot. Or if the D1 is between 1 and 3, C1 and C1 and C2, we will take the second sample. Okay, so we have the parameters here. N1, which is the sample size on the first sample. C1, which is the acceptance number of the first sample. N2 is the sample size on the second sample. And C2 is the acceptance number for both samples. We are using C1 for the first sample, but we are using the C2 for each sample. Okay, if the defective units in the first sample is greater than the acceptance number of the second sample, we are rejecting the lot at the first phase. But if it's lower than that C2 level, but greater than the C1 level, we will continue to take the second sample. And the third option here, if the number of defective is lower than the C1 level, acceptance level for the first sample, we will accept the lot. After taking the second sample, we are going to take another sample here. Let's say in this example, we are taking a sample size of 100, okay? And this D2 is the number of observed defectives in the second sample, okay? And if the number of defectives in the first sample plus number of defectives in the second sample is less than acceptance level of the second sample, we will accept the lot. And if this summation is greater than the acceptance level of the second sample, we will reject the lot. Okay, that's it. This is double sampling method. Advantage of a double sampling plan over single sampling is that it may reduce total amount of required inspection. Why? Because in the first sample, we are gonna take less sample than the single sampling plan, okay? And if we, for example, accept most of the time the lots, then we don't need to go with the second sample, so this will reduce the total number of inspections, okay? If there are lots of rejected lots, also we don't need to go with the loss of inspections. But if the number is between that range, we need to take another sample, but it will also increase the number of sizes when we compare it to the single sampling plan. But on average, we expect that the number of inspection will be lower. That's why we are doing double sampling, okay? Let's see it in OC curve. How can we calculate that? How can we draw that OC curve against the lot, fraction defective, and probability of acceptance? We will use that formulation. The probability of acceptance will be equal to the probability of acceptance of the lots in the first sample plus probability of acceptance of the lots at the second sample. Okay. For the first sample, we are going to calculate the probability of acceptance with the D1 values, and we will use here the C1 value, okay? So we will take, in this example, C1 is 1, then we are going to consider the defective units when they are equal to 0 or 1. So also we are going to use the binomial distribution formulation, cumulative distribution formulation, okay? For the probability of acceptance at the second sample, we will take two considerations in this example. The first consideration, if the D1 is 2 and D1, the number of defectives in the first sample is 2, and number of defective units in the second sample is less than 1, okay? This is the case, the first case, we are taking the second sample. Okay, second sample, taking second sample. here. We are taking second sample and accept lot. The first case, okay, D1 is what we have said. D1 is equal to 2, right? This is equal to 2. So D2 here, it must be 1 or 0, right? When this is 2, it won't accept a lot. That's why in the first case, if the D1 is 2, D2 must be 0 or 1, okay? In the second case, D1 will be 3, okay? When the D1 is equal to 3, we are not going to reject the lot. We are going to take the second sample, right? And when the D1 is equal to 3, D2 must be 0, right? Otherwise, we will reject the lot. But we are calculating the probability of acceptance. That's why D2 must be 0 when the D1 is 3. So this is the second case. So how are we going to calculate them? These are the intersection probabilities, but events are independent. So we are going to multiply the probabilities directly. The first case, when the D1 is equal to 2, we are going to take that calculation. For the second term of the first case, when the D2 is lower than 1, we are going to use the cumulative distribution, okay, that formulation. Then we are going to calculate the probability of acceptance for that case. For the second case, we are going to make the D1 is equal to 3, and we are going to make the D2 is equal to 3, and then we are going to calculate the probabilities of these events. We're going to use the binomial distribution, mass functions. Then we will calculate the probability of this second case. And the total of that first case and the second case will give us the probability of acceptance at the second sample. We have already calculated the probability of acceptance at the first sample here. Then the total of the probability of acceptance with the second, double sampling will be that value. So we can construct the OC curve with these calculations. In these calculations, we are going to use the lot fraction defective. When the lot fraction defective is increasing, the probability of acceptance will be, of course, lower for these values. Okay? So we have reviewed it. Let's continue. So how can we calculate the average sample number curve? So we said that in double sampling, we expect that we are reducing the number of inspections, right? Because in the first sample, we are not taking that much item in it, so we are reducing the inspection here. And if the acceptance probability is high, we will accept lots of, most of the lots. Then we will go with the second sample with low probability. So we expect that in average, we can reduce the number of inspections. So this calculation is important if we can achieve this reduced number of inspection or not. If we cannot achieve the reduced number of inspection, we don't need to go with the double sampling. It doesn't make any sense, right? We go with the single sampling instead of it. But if we can reduce the number of inspection in the double sampling, we can go with the double sampling. We can continue with it. We can use this sampling plan. But let us draw the average sample number curve first. But first, we need to calculate the values. To calculate the values, we will take the first sample. Okay, this is the first sample. The number of units in the first sample. And this is the P1, and P1 is the probability of making a lot disposition decision on the first sample. Either we accept the lot, either we reject the lot. Okay, so either the lot is accepted, either or lot is rejected on the first sample, and we take these probabilities and then summing them up, so we find the P1 value. Okay, and after that, if we pass through the second sample, then the total number of samples will be the N1 plus N2, right? The first sample size and the second sample size. If we go after the second sample, this will be the number of inspections we made. But for what case when we do not make any lot disposition in the first sample, okay? And the probability of this event is 1 minus P1, right? So when we simplify it, N1 plus N2 multiplies with 1 minus P1, all right? So we can draw our graph then. This is the R graph. But notice that here we have inspected all of the samples, right? In the first sample, we have inspected all of them. And if we couldn't make any lot disposition after the first sample, we go with the second sample. And we have inspected also all items in the second sample. This is the case, okay? Complete inspection, okay? So at the beginning, when the load fraction defective is low, okay, the average sample number will be lower than the single sampling. This is a single sampling, okay? This is a constant. We are just using a single sampling, okay? The average sample number will be lower than the single sampling. But when we, couldn't accept the lot easily in the first sample, okay, we will go with the second sample. And that's why after lot fraction defective, passes some point, then we need to take the second sample. That's why the total number of, average number of samples, average number of inspections will be increased, right? But after some point, it will reduce. Why? Because after a high point of lot fraction defective, we will start to reject the lots in the first sample, so we don't need to also go with the second sample. That's why it will reduce after some point. Okay. Also, we see here curtailed inspection. Curtail mean the decreased. Okay. By curtailment, we will try to reduce the number of samples we are taking in the double sampling. How? At the beginning, we have said that we are going to first take the first sample, and if it requires, we are going to take the second sample. And up to here, we have assumed that we have also made a 100% inspection on the second sample. But in practice, we can make curtailment. Curtailment means that when D2 is greater than C2, so the defective units in the second sample is greater than the acceptance level of the second sample, we can terminate the inspection and reject the lot immediately. So by this way, we can reduce the number of inspections in second sampling, and this is called curtailment, okay? However, in the first sampling of double sampling or in single sampling, the curtailment is not suggested because it will make prejudice to the lots and the supplier. For example, you have taken a sample size of 100 and you started the inspection. You have selected one item and it is defective and put it, in the shelf. And then you take another, item from the sample and it is also defective. And you put it on the shelf, let's say. And then you take another sample and it is also defective. And if your acceptance level is 2, then you need to reject the lot, right? Because it exceeds that acceptance level. But if you do not make 100% inspection there, and if you terminate the inspection immediately after you have observed the number of defectives up to exceeds the acceptance level, this will create prejudice against the lots and against the supplier, and people will believe that the rest of the lot also is corrupted. They are also useless. But maybe it is not the case. Because of random sampling, maybe the three defective just comes into the first initial inspection, maybe. So that's why in single sampling and the first sampling of the double sampling, we do not suggest to make curtailment. Okay, just go with the 100 inspection in this kind of samples. And average sample number with the curtailment, how can we calculate it? We can use that formulation. This is just similar to the previous calculation of the average sample number we can use, but we need to just add some extra steps. All right. And with the curtailment, see that the average sample number is always lower than the single sampling. So you can use curtailment in the double sampling. It's okay. How can we create a rectifying program in double sampling? We can make this, and we can use these two specifications, these two metrics. In the case they are so important, we have already mentioned previously. This is average outgoing quality in the double sampling, and this is average total inspection in double sampling. And we can use these formulations to calculate these numbers. All right. The other sampling plan is multiple sampling plans. It's like an extension of the double sampling. How are we going to use it? Let's say we have taken one sample, the first sample from the lot, and if the number of defective is greater than 0 but lower than the 3, we can go with the second sample. Then let's say we have just taken the second sample, and if the total number of defective units is greater than 1 but lower than 4, then we are going with the third one, and it continues like this. But after the fifth sample at most, we are just cutting the sampling. We can also make rejection and accepting of the lots, before the fifth sample. How can we do that? For example, in the first sample, if we encounter 0 defective, we can accept the lot. Okay, but also let's make another example. In the second sample, for example, if we encounter in total 5 number of defectives, we are just rejecting the lot. All right. This is the idea of multiple sampling plans. And also this is important. The first sample is usually inspected 100%, although subsequent samples are usually subject to curtailment. So this is also the case for this multiple sampling. In first sample, we are not doing curtailment like in double sampling. The last sampling plan, we are going to talk about sequential sampling plan. In sequential sampling plan, it's like multiple sampling. We are taking samples individually or a group of items. If the sequential sampling is based on items, individual items, it is called item by item sequential sampling. And it works like this. For example, we are taking a sample at the beginning, and then we are taking another sample, and then we are taking another sample, and this is the the number of items in the sample. Okay, this horizontal line. We are taking another sample and another sample and another sample, and this is the number of defectives in total in the samples. Okay, let's say we are at that point, and here, let's say, for example, we have taken 18 items, item by item. We have just taken one item, second item, third item, and the total number of defective units is here, for example, 1. Okay, so we are also counting number of defectives while we are taking the items from the lot. All right. And if this line, when we draw line by the sample number and the number of defectives, if we keep on this range, on this interval, okay, on this region, we will make sampling. We will continue to sampling. But if we, exceeds that line, we will reject the lot immediately. Or if we, falls out from that line, we will accept the lot immediately. So how can we draw these lines though? We will use these formulations. For the rejection line, we will use H2 plus S multiplied with N. And for the accept line, we will use minus H1 plus S multiplied with N. Okay? And so what are these H's and S, etc.? This is here. You can calculate the H1 value with this logarithmic function and H2 value by this. And in K value here, there is a K value, and K value can be found by that formulation, and S value can be calculated by that formulation. At the end of these formulations, you can construct the lines, acceptance line and rejection line like this. Then you can start the sampling sequentially. Okay. For example, suppose that we wish to find a sequential sampling for plan for which P1 is 0.01 and alpha risk is 0.05. This is the P2. You can remember from this, probabilities lot defection percents from the previous slides. And this is the beta risks, let's say. And then we can find this K, H1, H2, and S values by the logarithmic functions. Then we can draw our lines, exception lines and rejection lines, okay? Also, without drawing, if we put this, numbers against our number of defectives, also we can find the regions for the rejection or accepting the lots, or maybe we can in between them, so we can continue to sampling. Okay. All right. Let's continue. And also in sequential sampling, we can calculate average sample numbers. Okay, with these formulations, and the expansion of the formulations are given with this logarithmic functions, etc. And if we use rectifying program in the sequential sampling, we can use this average outgoing quality and average total inspection calculations by making these computations. Okay, so it also applies for the sequential sampling. All right. So that was it for the sampling plans. Lastly, let me talk about this. And up to here, we have seen lots of tools, right? Lots of computations and indicators, factors, etc. They are important, right? And these tools are coming from a standard, actually. This standard is based on after World War II. It's a military standard. Okay, they are widely used for acceptance sampling system for attributes. And lastly, recently, these military standards are also civilized and adopted by the ISO, standard systems. And the code of the ISO standard system for accepting sampling for attributes is 2859. If you are interested in this ISO documentation and ISO standard systems certification, etc., you can check those standardization systems also. All right. So earlier we said that we can use diagramic sampling plans table, and you can find these tables in the textbook. These tables are huge. I didn't put it here. You can find the tables in the textbook. Also, you can search the tables in the Google. You can find them. And these tables are like reference tables you can use, and you can design your sampling plans by finding the specific average outgoing quality level and by finding the lot tolerance percent defective protection level for your case, okay, then you can design your sampling plan according to that tables. But here, let me say this. When we compare the LTPD protection with the average quality level, when we compare these protection levels against the bad quality of the lots, we will go with the, especially maybe we need to go with the lot tolerance percent defective. Why? Because accepted quality level can lead some misperception. And why the accepted quality level is not good, we can also see in the defective parts per million scale. Also, let's give an example here. For example, suppose that a printed circuit board contains 100 elements in it, and each manufactured by a process operating at 0.5 defective. If the accepted quality levels for these elements are 0.5%, and if all elements on the printed circuit board must operate for the card to function properly, then the probability that a board works is this, 0.6. It is low, it's very low, right? So thus, there is an obvious need for sampling plans that emphasize LTPD protection even when the process average fallout is low. The Dutch ROMIC plans are often useful in these situations, so we can use LTPD protection and LTPD protection. You can remember we were focusing on the individual isolated lots. We were not dealing with the stream of the lots. All right. So here it also suggests maybe we can go with the LTPD instead of using accepted quality level indicator. So that was it. Thank you.